Good afternoon, all of you. In thermodynamics, we were speaking about enthalpy or enthalpy in different situations. In previous class, we discussed about reaction enthalpy, standard enthalpy of reaction, and about enthalpy change during phase transformation. And in today's class, we will be discussing about standard enthalpy of formation. We studied about standard enthalpy of reaction, and today we will be studying about standard enthalpy of formation. So it is very similar to that of standard enthalpy of reaction, but there is a slight difference for that. So in standard enthalpy of reaction, we told it's a change in enthalpy between reactants and products. So it is same in case of standard enthalpy of formation also, but the slight changes here we consider 1 mole of compound formation from its elemental forms. So in standard enthalpy of reaction, we spoke about any reaction with which the reactant and product should have an enthalpy difference. But in standard enthalpy of formation, what we are telling is the reactant should be in its elemental form and its most stable state or standard form, and the product should be 1 mole. So when 1 mole of product is formed from the elemental form of reactants and that too in the standard state, then we can tell the difference between these two or enthalpy difference between these two will give us the standard enthalpy change of formation. Yesterday we studied about what is standard condition and how it is represented. Now we will consider an example. So this is a condition or a brief condition for a reaction to show enthalpy of formation. So 1 mole of compound should be formed from elemental most stable states. So that is a condition for a reaction to show standard enthalpy of formation. And we will consider this equation. And always remember, when we consider a reaction, we are taking molar equations. So here we tell 1 mole of H2 reacts with half mole of O2 giving 1 mole of H2O. We don't tell 1 molecule of H2 reacts with half molecule of O2. So if we tell half molecule of O2, then it will be O, oxygen itself. So it becomes an oxygen atom and it loses the property of molecule. So we can't tell it's a half molecule. Whenever we speak about enthalpy of formation, we speak about the molar equation. And the enthalpy of formation is represented by delta F, H and this symbol for the standard state. And the enthalpy of formation of this equation is minus 285.8 kilojoule per mole. So when we check the conditions, whether these are in the elemental form, yes, they are in the elemental form, hydrogen and oxygen, that too in the pure gaseous form, which gives H2O liquid, and 1 mole of H2O is formed. There is no number here, so it is 1 mole of formation. So all the conditions are satisfied. The conditions are 1 mole of compound should be formed. Here we don't consider what we take. When we consider this side, it should be 1 mole and reactants should be in elemental states and two most stable states. So all the conditions are satisfied. So we can consider it for a enthalpy of formation which is negative 285.8 kilojoules per mole. Now we will consider the next equation. Carbon in its graphite form. So it is the most stable form of carbon which is graphite solid plus 2H2, 2 moles of hydrogen gives CH4. So here when you write it as a capital hydrogen. So CH4 which is methane gaseous form. So what are the conditions? 1 mole of compound is formed. Is this 1 mole? Yes, it is 1 mole of methane which is formed from elemental form or most stable state. So carbon and hydrogen is in elemental form and they are in the most stable form. Hydrogen is in the gaseous form and carbon is in its graphite solid form. So all the conditions are satisfied. Then we can tell it will have an enthalpy of formation which will be negative 74.81 kilojoules per mole. So this much of enthalpy change is carried out there. And with this, we can understand one more fact, whether this is exothermic or endothermic reaction. So when the formation enthalpy is negative, which means the energy is given out. So system is becoming negative means energy is going from that. So it is a exothermic reaction. In both the cases, we have an exothermic reaction. And here another reaction, graphite in its elemental form, hydrogen also in elemental pure form, oxygen also in elemental form, giving 1 mole of product. So we can tell this equation is also will have delta enthalpy of formation. So change in enthalpy will be negative 277.7 kilojoules per mole. That is also an exothermic reaction as we have negative enthalpy. So standard molar enthalpy of formation, delta formation, is just a special case of delta RH. This we have told. So formation enthalpy is actually a special case of enthalpy of reaction only. So when the enthalpy of reaction is told in 1 mole of formation, and when it is from the elemental form, we can tell it's a enthalpy of formation. So enthalpy of reaction in its elemental form forming 1 mole of compound, it's a enthalpy of formation. So if we consider this example, CaO plus CO2 gas gives CaCO3. So in this reaction, we cannot tell the enthalpy of formation because the conditions, if you see, this 1 mole is formed, that is proper. So 1 mole of CaCO3 is formed, so that is no mistake. But here if you see, reactants are also in compound form. They are not in its elemental form. It's carbon dioxide and calcium oxide. They are not in the elemental form. Hence we cannot tell the enthalpy of formation. We can just tell the enthalpy of reaction for this particular reaction. So when there is elemental form of reactants which is in the pure form, and when we have 1 mole of product formed, then only we can tell it is delta FH or enthalpy of formation. Otherwise we just tell enthalpy of reaction, which is negative 178.3 kilojoules per mole. So that is also an exothermic reaction. Another condition, so we will consider this reaction, H2 plus Br2 gives 2 HBr. Whether this reaction will show enthalpy of formation. So the conditions are 1 mole of compound should be formed from its elemental stable states. So in reactant part, if you see, you can see the elemental forms of reactants which reacts to form HBr. But there the problem is the formation is for 2 moles of HBr, and it will show enthalpy of formation only when there is 1 mole of compound which is formed. So we cannot tell enthalpy of formation of this reaction, we can only tell of enthalpy of reaction. So enthalpy of reaction we can tell for this reaction, not the enthalpy of formation. But this reaction can show enthalpy of formation when we do a slight change to this. Elemental form is correct, but number of moles only is the change. In that case, we can do a slight change to this reaction to make it show enthalpy of formation. So if you divide the whole reaction by 2, then here also we will get 1 mole of HBr. Hence, the reaction will be half of H2, half moles of H2 plus half moles of Br2 giving 1 mole of HBr. Now the conditions are satisfied. Formation of 1 mole of compound from its elemental and most stable states. For this reaction, we can tell enthalpy of formation. And one more fact is, enthalpy of formation of an element in its most stable state is taken as 0. So for elemental states, the delta H of value is actually 0. So whatever value is present for this, or for example if we consider the delta H of value of this reaction is minus 36.4 kilojoules per mole, and this value is actually given by the product, because elemental form will not have any delta HF value or enthalpy of formation value. So for the whole reaction, whatever value we get is actually given out by this part, as this part, the elemental form, will have delta HF value as 0. So this part is 0. So whatever value we get is this value, or the responsibility of this value is for the product part. Now we will see where exactly we need this enthalpy of formation, or where in a question we can apply this values of enthalpy of formation. So we have a question there: how much heat is required to decompose calcium carbonate to lime and carbon dioxide? So it's a decomposition reaction. The formation reaction of the same compounds we have seen a few slides earlier, and that same reaction, just reverse reaction we are seeing here. It's a decomposition reaction of calcium carbonate to calcium oxide, CaO, or lime, and carbon dioxide, with all substances in their standard state. So they are actually asking about the standard enthalpy of reaction. So we will see the reaction. CaCO3, the calcium carbonate, gives, so reactant part is this, and the product part is CaO solid plus CO2 gas, and we need to find the delta RH. So when we know the enthalpy of formation of this compound and of this compound and of this reactant, then we can substitute that to the equation. So delta RH, or enthalpy of reaction of this particular reaction, is equal to summation of enthalpy of formation of the products minus the summation of enthalpy of formation of reactants. So that is the equation we have, and A and B are the stoichiometric coefficients. We don't have any stoichiometric coefficients here, so because of that we don't use that A and B term. So the standard enthalpy of reaction is equal to enthalpy of formation of CaO, or the energy required to form CaO from its elements, that we are substituting here, plus enthalpy of formation of CO2, the energy required for the formation of CO2 from its elements, that we are summing. So the product part is done. Enthalpy of formation of CaO plus enthalpy of formation of CO2 minus enthalpy of formation of CaCO3 from its elements. So this is the equation what we have, and the values for this we will get from the references, like the table which is given in your textbook. So from that we are substituting the values. It will become 1 into, so this 1 is for the CaO, the stoichiometric term. Here when there is nothing, we are substituting 1 here. So 1 is the stoichiometric coefficient. 1 into negative of 635.1 kilojoules per mole is the enthalpy of formation of CaO. That we substituted, and with the minus sign we will understand that it's an exothermic reaction, plus 1 into negative 393.5 kilojoules per mole of CO2. So to form CO2, enthalpy of formation required is negative 393.5 kilojoules. So it is also an exothermic reaction. Summation of this minus 1 into that of reactant. So to form CaCO3 from its elements, it needs negative 1206.9 kilojoules per mole of energy. It is also an exothermic reaction. So after the calculation we will get the value of 178.3 kilojoules per mole, because after this the negative and negative, it will become a positive value. So negative 635 plus negative 393 plus 1206 will give us this value, positive 178.3. So that means we got the amount of heat or amount of energy required to decompose calcium carbonate, and that's a positive value. Hence, we need to provide it to the system. It's an endothermic reaction. So we need to provide this much of energy to calcium carbonate to form CaO and CO2, or for decomposition of calcium carbonate we need 178.3 kilojoules per mole of energy. So this is the situation where we use the enthalpy of formation values. So with this we wind up our class. So please prepare notes and submit. Thank you.